Teste.
Okay. Ladies and gentlemen, good morning. It's with great pleasure that we welcome to our guest speaker, Professor Stefan Tenbohlen. Today he will present the lecture entitled Reliability and Condition Assessment of Power Transformer. Professor Stefan received his diploma and doctoral engineer degree from the Technical University of Aachen, Germany, in 1992 and 1997, respectively. In 1997, he joined to Alstom, Germany, where he was responsible for basic research and product development. From 2002 to 2004, he was the head of Electrical and Mechanical Design Department. In 2004, he was appointed to a professorship and head of the Institute of Power Transmission and High Voltage Technology of the University of Stuttgart, Germany. In this position, his main research fields are high voltage technique, power transmission, and electromagnetic compatibility. Professor Stefan holds several patents and published more than 600 papers. He is member of IEEE SIGRE Study Committee A2 Power Transformer, German Committees of A2 Power Transformer and Reactors, D1 Materials and Emerging Test Techniques, C4 Power System Technical Performance, several international working groups. Furthermore, he is convener of SIGRE Working Group A2 Analysis of Transformer Reliability. Thank you very much, Professor Stefan. I know that your agenda is quite a bit hard, and thank you for being here in Santa Maria with us, giving us this speech at Sepoc. Thank you very much. It's your turn.
Yeah, Tiago, thank you very much for the introduction. Yeah, bom dia. That's almost all I can speak in Portuguese language, so unfortunately I have to continue in English, and but I hope that everybody will understand what I'm talking here. So once again, thank you for this honorable invitation here to Brazil. You know, as I left the university and started my industrial career with, at that time with Alstom in Germany, I had a lot of business here with Brazil because I was responsible for the development of online monitoring systems, and we had several installations here in Brazil. So let's say 20 years ago, I was used to travel every 2 months to Brazil. Unfortunately now, the intervals are a little bit bigger, yeah, but I really enjoy being here. Yeah, so what will I talk about? I will talk about power transformers, yeah, and you know, I know that this conference is about power electronics, so you could ask, why are we talking about power transformers? Because power transformers is a technology which is more than 100 years old, and so I would say power transformers are not the most sexiest equipment in the world, yeah? So why talking about power transformers? Yeah, because we are designing now the power energy systems for the future. And because we want to reduce CO2 emissions, a lot of sectors has to be electrified. Yeah, so the vehicles should not use any more combustion engines, they should electrical motors. also heating in the houses should be done by electrical energy in order to save, of course, CO2 emissions and not to spoil the fossils as coal or oil. But if you want to electrify a system, then of course you need transformers, because transformers are the basic elements for transmission of electrical energy. And in Germany, this means that in the distribution sector, in the next 20 years, 80% of the distribution transformers have to be exchanged. And if you go here a little bit around and you see all these distribution transformers, you can imagine that this is a very huge number. So in the distribution system, it means for Germany roughly 500,000 new transformers, which has to be exchanged in the next 20 years. And this is a tremendous task, because there is not a production capacity of these transformers. If you want to buy at the moment a 100 kV transformer, so a bigger unit of, let's say, 40 MVA, it takes you at least 4 years, because all the manufacturers in Europe are fully booked. So to build all these transformers is, let's say, nearly impossible, because the production capacity is not that high. So what does this mean? You have to use the old transformers for a longer time, and additionally, maybe you need higher loading of these transformers, so loading beyond the nameplate rating. And if you do so, of course, if you use older transformers, the failure rate can increase. So it's important to investigate first, what failure rates do we have, at which ages transformer fail, and then, of course, how can we assess the condition of the transformer? And that is what I'm talking about today. I will start first with analysis of AC transformer reliability. This is the short version of a tutorial of SIGRE. So SIGRE is, I would say, the biggest association, which is a worldwide association, which is dealing with transmission and distribution of electrical energy. So there are thousands of experts organized within this SIGRE, and within the SIGRE there are several working groups dealing with specific tasks. And we started shortly before the pandemic with this working group, AC transformer reliability, and I was the convener of this working group. Such a working group has roughly 15 to 20 members, and so we worked 3 or 4 years on this topic, and the results of this working group are shown in a technical brochure. You can see here this technical brochure, which is available on the SIGRE platform. And additionally, we have done this tutorial and present this tutorial worldwide to the people who are working with transformers. So, and today I will present a short version of this tutorial, and afterwards I will go on the and continue with the condition assessment of transformers. So what can you do to assess the condition of a transformer? So let's start with the SIGRE tutorial. And of course you could ask, what is the motivation to do failure analysis? But you know, the accurate information about the service experience of high voltage equipment is of course of high importance for manufacturers and also operators. You know, manufacturers can improve their products if they know why they fail. Then you can strengthen the weakened points of your products. Secondly, the operator has to know what is the reliability of its system. Also, he can benchmark the performance of its components to the components of other network operators. And last but not least, standards for the product are improved based on the operational experience with this equipment. So it is quite important to know how often failures and why failures occur within power transformers. In the brochure we have a large chapter written, for example, what measures you can do in a transformer to increase the reliability. Simply this would have been too much for, let's say, for this 25 minutes where I will talk on transformer reliability. So I will just explain here why and when transformers fail. Yeah? And in order to know this, of course, you have to ask the utilities, when and why do your transformers fail? So we established a questionnaire to collect this failure data. And before you start, first you have to define what is a failure. And we said a failure is something where the transformer is more than 7 days out of operation. Yeah, so maybe it can be repaired, or it must be scrapped. Yeah, but it's like it's not if, for example, a relay for controlling the cooling unit fails. This is not a major failure. Yeah, you can exchange the relay and everything is fine again. A major failure requires oil treatment. Yeah, you have to release the oil from the transformer. You have to exchange the bushing. These are major failures. And then we ask the utilities for data. First, you need also information about the living population of the transformers. Yeah, so if you want to assess what is the failure rate, of course you have to know how many transformers are operating in the network. Yeah, and so we ask, and also how old are these transformers? Yeah, and so the operators had to fill in such an Excel sheet where they had to write down how many transformers they commissioned in each year in different voltage classes. Yeah, from this, let's say we got the age distribution of the transformer population of this respective utility. So, and then of course we collected the data about the failure itself. Yeah, so the operator had to do this with this Excel sheet, and with this Excel sheet we have here these pull-down menus where you can select reasons and location of the failure. So you do not have to write it down, you just select from a list, which makes the statistical analysis much easier. Of course, we collected information about the year of manufacture of the transformer, the voltage, the rating, and some additional information. And we sent out this questionnaire to utilities in the world and collected the answers. The questionnaire itself is also, you can download it with this link. In case you are an operator of transformer, maybe this could help you a little bit to track your failures in your company. So let's come to the analysis of failures. So in this table you can see the number of responses. So in total we got responses from 66 utilities in the world. Most of the data came from Asia and Europe and America. America was unfortunately almost the data from North America. So South America was not that strong this time. In total, we collected 1,200 failures, major failures. We also collected retirements. Yeah, so sometimes utilities retire a transformer. So let's say they do not wait until it fails, and the number of retirements was a little bit higher. That was almost 2,000 transformers. This was based on a fleet of almost 40,000 transformers. So transformers with a voltage higher than 100 kV. So it's already a considerable amount of data we have collected. Most of these transformers are substation transformers, so, or you can even call them grid coupling transformers, not generator step-up units. Yeah, you know, a generator step-up unit is located in a power station, and normally such a generator step-up unit is stronger loaded as a substation transformer. Yeah, the grid coupling transformers have normally during operation a lower load, and the effect is of course that the aging of these substation transformers is also less. Yeah? So the data I'm now presenting is 96% based on substation transformers. So what you can see here is the age profile first of the in-service transformers. Yeah, so the transformers which are still working. And yeah, we can see here, let's say we have a considerable amount of data up to 60, 70 years, age of transformers. The average age of the fleet is 25 years, yeah? But the oldest transformer we have in our database, that is the nameplate of the transformer. This one, the nameplate is difficult to read, but this transformer was manufactured in 1919. So it has more than 100 years of operation, and it's still operating. And it's operating in North America, yeah? So they can be proud to have the eldest transformer in the grid. Yeah, so if we go to the failure rates, on the left graph we can see the rate of failures. You can calculate this rate of failures if you divide the number of major failures by the number of the transformers which are operating multiplied by the time of your investigated interval. Yeah? And we investigated failures between 2010 and 2019. So 10 years, and we had to multiply this 10 years then by the number of transformers, 40,000 transformers in our database. So we have basically 500,000 transformer years as operating experience and a little bit more than 1,000 failures. And this brings us to an average failure rate of 0.3%, something like that. So it's a quite low value, yeah? And we can see here the dark green bars are the substation transformers. You can see that the failure rate is increasing with the voltage class. Yeah, here on the x-axis you can see the voltage class, and for voltages more than 700 kV we have a failure rate of almost 1%. There's also the failure rate shown for shunt reactors and for generator step-up units, but as I said before, the number the population of GSUs and shunt reactors was quite small. Therefore, let's say these data is maybe not so accurate as for substation transformers. Yeah, but you can see here for GSUs, which is the red bar, it's much higher than for substation transformers. You can say more or less double failure rate of generator step-up units compared to substation transformers. If we go, but let's say the average failure rate here, let's say it's 0.3%. What is the meaning of 0.3%? If you have, let's say, a population of 300 transformers, it means one will fail in a year. So I would say the reliability is quite high. So this is really a good value, I would say. On the other hand, we investigated also the retirements. Retirement rate is a little bit lower than the failure rate. I don't think that it is necessary to go here too much into the details. We analyzed also the location, so where did the failure occur? And you can see here the biggest percentage is windings, winding to ground insulation, face-to-face insulation. So let's say more or less failures in the insulation system. Basically, this is, let's say, half of the failures. And then we have, of course, also failures in bushings and tap changes. This means that for the condition assessment of a transformer, you have to investigate not only the active part, the windings, but also bushings and tap changes. Yeah, that is important for the condition assessment later. We also checked the failure cause. So what is the reason why transformer failed? And this is often a tricky question. Yeah, because at the end of the day, you have there a transformer which failed. You have to replace this transformer, so often the focus is on the new transformer which is put there in the substation, and the failure investigation is, I would say, not properly done. And this reflects also the results of this question. So, we have a lot of suggestions which failure could have been. So short circuits, over voltages, overloading, aging, design, maintenance. So let's say we thought that we have given all reasons for failures. Nevertheless, 23% of the failures are due to other reasons. Unfortunately, I do not know any other reason which could be possible, but 23% is other reasons, and 16% is unknown. So we guess that the people didn't want to say unknown, so they cross-checked here other reasons. Yeah? So this shows that failure investigation is not properly done. Yeah? And of course, this is quite important, yeah, because if you want to improve a product, you have to know why it fails. So that is one of our suggestions to the operators, that they do a proper failure investigation. Biggest contributor in this case here is external short circuits. So 13% of the failures are related to external short circuits. This is quite important information, because at the moment there is the revision of the respective ISC standard planned. In this ISC standard there is written how to check the short circuit performance, and if a lot of failures are occurring due to short circuits, you have to maybe adjust the standard a bit to improve the product. Statistical techniques and hazard curves. So we look now why transformers fail, where are they failing, but we didn't check when they are failing. Yeah? And for the question when, we need these statistical techniques. As I said before, we collected the age distribution of different populations. So we investigate the populations of different continents. Here you can see the age distribution of Australia and New Zealand, and the lower graph, North America. And what you can see is that here, of course, in North America, the age of the transformers is much higher as in Australia and New Zealand. And the answer is not that Australia is using electrical energy just since 20 years or so. Yeah? So they also have since 100 years an electrical network. But in Australia and New Zealand, the regulator gives money to the operator to exchange the transformers after a certain time. That is the reason this country has a quite high retirement rate, but also a very young fleet of transformers. Yeah? So the average age in Australia and New Zealand is just 18 years. In North America, it's more than double. And as I started, let's say, working with power transformer, it was always said the average age or the expected lifetime of a transformer is 30 years. So the design should be as good to survive 30 years. And if you go to North America, you can see the average age is already 37. Yeah? So more than 50% are exceeding the 30 years. So normally, if that rule would be applied, yeah, most of the transformer had to be exchanged. Here are the other continents. Maybe also, of course, South America is interesting. I have to say that from South America, we just received data from Brazil. But unfortunately, I would say not sufficient data. Yeah? So we have here the eldest transformer is just 36 years old. But I'm pretty sure that in Brazil there are transformers which are much older than 36-year-old. And I tell you, 20 years ago I was installing here new transformers in Brazil, and a considerable amount of transformers. And if you go here now for 20 to 26, there are almost no transformers. So it's clear that this statistic is not covering all the transformers. The problem with collecting of data was, of course, that we had to do this during the pandemia, yeah, and at these times you could not travel, you could not go to conferences, you could not meet people in person, you just could send emails, yeah, and you know what happens if you send an email, yes, and especially if you ask for data, because this data means a lot of some work, and so the emails are forgotten and you do not get any answer. Yeah? That was a little bit problematic. So, but statistical things, especially for the students, you can do lifetime analysis based on Weibull distributions. Maybe some of you heard about Weibull distributions. This is, let's say, the equation for a Weibull distribution. This Weibull distribution describes, in this case, the failure rate over the age of the equipment. Yeah, and if we look here at this formula, you have these two parameters, beta and eta. Beta is the shape parameter. And you can see here the influence of the shape parameter. Yeah, if the shape parameter is smaller than 0, this is a dark green curve, you can see that in the beginning you have a high failure rate, and then the failure rate is decreasing. And this is typical problem for typical sign for teething problems. So you have high failures in the beginning. Yeah, let's say you buy a new equipment, you switch it on, and it fails. These are early age problems, and this happens if, let's say, the quality check process during manufacturing is not okay, testing is not okay, yeah, then you have failures quite early in the lifetime. If beta is 1, yeah, that is a light green curve, then the failure rate is constant over the lifetime. And this means that the failures are more or less random failures. If it's bigger than 1, here as an example, beta equals 3, then you have here such an increasing failure rate with age, and this is of course a sign of aging. So, if you now investigate when transformers fail and you use this statistical data to plot the curve, and then you fit these data with such a Weibull distribution, and your beta is 1, then you know it's more or less random failures. If beta is bigger than 1, then you have aging behavior in your equipment. Of course, both happens. So you have random failures, you have infant failures, and you have also aging failures. Yeah? So let's say 3 different distributions show the full failure processes. Before I come back to the transformer, I have to explain a little bit more with the Weibull distribution. In the former graph, I showed the failure rate. Here, we are using the cumulative distribution function, also called CDF. And this CDF shows which fraction of the population failed already. Yeah, so if we have here, for example, again, beta equals 3, and we say eta is 50 years. Yeah, I didn't explain eta up to now. Eta is the so-called characteristic life. Yeah, and this is a, we call it the scale parameter. Yeah, because it scales, yeah, the length of the time. And for this beta equals 3 and eta 50 years, it means that here, of course, you have an increasing failure rate, and let's say after 80 years, almost 100% of the equipment has failed. When 63% failed, which is here 50 years, you can see so eta is the 63 percentile. Yeah, so that is a year when 63% of the equipment failed. Interesting is, if you use logarithmic scales, here like in the right figure, yeah, so we have here a logarithmic scale for the lifetime and also the logarithmic scale for the fraction failing, then this curve develops in a linear graph. Yeah, and of course such a linear graph can more or less easier be evaluated. Yeah, so the increase of this line reflects beta. Yeah, so if we have beta very low, we have here a very low increasing line. Yeah, with beta equals 3, it's going here. If you change the characteristic life, this curve or this line is shifted to the right or to the left. Yeah, just to understand the Weibull distribution. Okay, now this function we used for the statistical analysis, and in this case you can see the retirements. So we checked after which year a transformer was retired. Yeah, and for each case we have one of these dots. So, and these dots we fitted with a Weibull distribution, let's say with 2 Weibull distributions. So in the first 20 years, you can see here a line which corresponds to 0.9 as beta and 24 to eta. And after 20 years, beta increases to 5 and with eta 79 years. Why is it in that way? You know, normally you do not retire transformers when they are young. Yeah, so this is a random event to retire a transformer quite early. Maybe you have to retire it because of condition, but maybe also because of network conditions, whatever. Yeah, so then you have these cases here. And after 20 years, if you have a problem with a transformer, you could think, it's already quite old, and maybe it will fail, and therefore I will retire it. Yeah, so of course, if a transformer is older, the engineer thinks, it will fail, and maybe repair is too expensive for such an old transformer, so I retire it. So the probability of retirement is, of course, much higher if the transformer is older, and that you can see here in this figure. Okay, but we are not interested in the retirements. We are interested, of course, in the failures. And here you can see the Weibull distribution for the failures. And here we have again two different distributions. So one with beta equals 1.2 and then beta equals 3.5, but with a characteristic life of 140 years. So, more or less, the transformers fail due to random events. So there is not a distinct aging behavior. Yeah, you could say 3.5 shows aging, but a very big scale factor. So 140 years. I said in the beginning 30 years is the expected lifetime of the transformer. Here we have, from the statistic, it shows it's 140 years. Yeah? So the North Americans did it correct. 104 years, no problem for a transformer. Let's keep it in operation. Yeah? So transformer failures are due to random events. And this means time-based maintenance. So the idea to exchange a transformer after 30 or 50 years is nonsense for transformers. From economical reasons, this is not good, because it can survive much longer. But, of course, you have to check the condition of the individual transformer. So you need a condition-based maintenance instead of a time-based maintenance. Yeah, and this brings me almost to the second part of my presentation. So that is the reason we need condition diagnosis for transformers, because they fail more or less randomly. So let's come to the conclusion. The transformer failure rate decreased compared to the last statistics 10 years ago. I didn't show you the second last statistic of 10 years before. That would have been too much. But the one result was that the failure rate is decreased during the last years. Winding-related failures are the biggest percentage in failure locations. The age distribution of the investigated population shows significant difference between the continents. And so we recommend not time-based maintenance. We could recommend condition-based maintenance, so diagnostic measurements and online monitoring. Also, utilities should more focus on failure investigation. And third, it is also necessary to give the regulators, let's say, a better understanding when transformers should be retired. This was, let's say, the first part of my presentation. In the second part, I want to explain a bit more. segundo? In the second part, I would like to talk a bit more on how can condition assessment be done. And yes, thanks. And there are a lot of diagnostic techniques available for power transformers. Yeah, I have written here, let's say the the most important diagnostic techniques. You can apply these diagnostic techniques offline and online. What does it mean, offline and online? For an offline method, you have to disconnect the transformer from the network, and then you do the measurements, and after the measurements you have to reconnect the transformer. So let's say the result is just the situation at this moment, which is normally, of course, not under load, just under voltage, but you do not have load on the transformer. And the big disadvantage is, of course, you have to disconnect and switch off the transformer. This is often a problem, that because these transformers are needed, and so offline measurements are sometimes difficult to perform. The other measurements are online measurements. Online means that the transformer is connected to the network. So let's say you have the normal operating condition of the transformer, and you can then go with your measurement technique to the transformer and measure, let's say, for 1 day. Or also you can keep the measuring technology at the transformer and you monitor the condition over a long period. In this case, it is called online monitoring. We have here a lot of diagnostic techniques. I will talk today about frequency response analysis and about partial discharge measurement. That should be sufficient. Let's start with FRA, frequency response analysis. Here I would like to explain first what is frequency response analysis, how is it performed, and second, which is, let's say, a very important issue at the moment, how can I interpret the results of a frequency response measurement. So first of all, you have mechanical forces on the winding. If you have a conductor and a current is flowing through the conductor and it's within a magnetic field, you have forces on the conductor. That's the principle of an electrical motor. And of course you have in a transformer a magnetic field, and you have also conductors where current is flowing. And in case you have, for example, a short circuit, the current is very high. And then also quite strong forces appear on the windings. Yes, there are, for example, radial forces, which means the inner windings are pressed to the core. The outer windings, there's a force outside. You have also axial forces, so the winding is compressed. And if the mechanical strength is not sufficient, the winding can be deformed. One is due to the radial forces is buckling. So normally the winding is round, but it can be that you have this type of buckling. Maybe I can show some pictures. So here you see a buckled winding. This is the low voltage winding of a generator step-up unit. And this is a view from the bottom to the top. And you can see here that there is such a buckle. So one part of the winding is pressed to the inner, the other is to the outside. And then you have this problem. Or conductor tilting. Yeah, here conductors, due to the compressional force, are tilted. We have all collapse of winding end support. Yes, so at the end of the winding you have thick wooden plates to press the winding, and here in this case this wooden plate is broken. Spiraling is the winding itself is turned. This all is done due to excessive currents in the winding. So, but it is of course difficult to detect these failures because you cannot see the winding. Yeah, the windings are in a steel tank, so you cannot see that. So the question is, how can we measure this from the outside? And for this purpose, we have the frequency response analysis. What is the basic idea? Yeah, if we have here, for example, two windings, this is a low voltage winding, we have here the high voltage winding, then of course these windings has inductance, also resistance, and these windings have capacitance to the other winding, also to the transformer tank, to the core. So it is more or less an LCR circuit. Yeah, and here I've shown a quite simple equivalent circuit of the winding, maybe from the first term lectures. You remember the equivalent circuit of the transformer, yeah? So this is mainly these elements with the resistors and the inductances. But if this equivalent circuit of the first term is just valid for one frequency, so for 50 or here 60 hertz in Brazil, and not for other frequencies. But for the frequency response analysis, we have to analyze a lot of frequency, a full frequency band. So of course we also have to add here capacitances, yeah, which you can see here in this equivalent circuit. Yeah, and of course such an LCR system has a response if you excite this system of capacitors, inductances, and resistors. So if you apply, let's say on one side, a sinusoidal voltage, the system will respond with, again, with a sinusoidal system, sinusoidal signal, with exactly the same frequency as the excitation signal, because an LCR system is a linear time invariant system. Yeah? So frequency is not changed, but the amplitude is of course changed. Yeah? So the response signal is a blue curve, which is smaller as the excited signal, and you have maybe also a shift of the phase angle. Yeah? So these are the two modifications in an LTI system. Amplitude is changed, or phase angle is changed. And for the frequency response analysis, we evaluate this frequency spectrum here. Because if you have a mechanical deformation, the capacitances in the winding are changed. And if you change the capacitances, of course also the resonance frequencies of these windings are shifted. Yeah? So if you can see here, for example, here at 1 megahertz, a resonance frequency, and you change the capacitances within the winding, this resonance is shifted to lower or to higher frequencies. Yeah? And once you detect such a shift of frequencies, then you can say, there's a problem inside the transformer. Let's come to the measurement setup. How do I measure the frequency spectrum of a full winding? Normally this is done with a so-called end-to-end measurement, because of course you have access in the winding only to the end of the winding. Yeah, because the winding is in the transformer tank filled with oil, so you cannot measure somewhere in between. Just the ends of the winding are brought to the bushings, so you can connect your measuring system to the bushings. Yeah, we have now here the measuring equipment. This measuring equipment has a signal generator, so it generates sinusoidal voltages which are applied here to one end of the winding, and the other end here is the neutral, and we measure the response on the other end, and we measure here also the voltage at the connection point, at the bushing. Because of course we do not want to measure the frequency response of the signal line. Therefore we have to use a dedicated measuring cable for measuring the input voltage. Yeah, and you know, a bushing is a quite long thing. Yeah, so if you know an oscilloscope, you have there the BNC connector, and this BNC connector has in the middle, the voltage signal, and the outer part is the ground connection, the shield of the cable. Yeah, but a transformer does not have a BNC connector. The ground is here at the tank. Therefore, you have to use the grounding strap to bring here the ground to the measuring cables, because the measuring cables, of course, are also shielded, and must be grounded. Okay, so you measure the applied voltage, the source voltage, and the response voltage at different frequencies. And for each frequency, you calculate the ratio between response and source. And if you evaluate the amplitudes, then you get the frequency response analysis, the curve. There are different ways to apply the voltage to the windings. Yeah, so you can apply it to the high voltage winding, to the low voltage winding. You can short circuit the secondary, or you can leave it open. You can measure the response voltage also on the other voltage level. So there are different setups. This is described in a standard which setups are possible. I do not want to go too much into the details of these connections. But what is important is, you know, FRA is used as a comparison. I need a fingerprint measurement when the winding is okay. Then I repeat the measurement later, and then I compare both measurements to see is there any shift of resonance frequencies. And if there's a shift, then I have a problem. If the curves are the same, everything is okay. But in this case, it means, of course, that you can reproduce your measurement very well. Yeah, and you know, if you change your measuring setup, of course, this can have an effect on the measured response. So it must be it is very important to keep the measuring setup constant. And these are some influencing factors for a measurement. Will not explain all these, but maybe I can show one thing, which is this connection from the tank to the cable, this grounding connection. Yeah, here we have a grounding cable which is not directly parallel to the bushing like here, but let's say you have here, it's just freely hanging under the bushing. And of course, if you have such a loop here, such a loop means an inductance. And an inductance, of course, influences the frequency spectrum. Yeah? So if you do the measurement like this, and the next time you do it, maybe the loop is a little bit bigger or a little bit smaller, you are changing the inductance of the measurement, and therefore also the frequency response. And then you have two different curves, and then you have to decide, is the difference because of a failure inside the transformer, or is it because this loop is different, and therefore it's strongly recommended to have such a tight grounding strip. This is one thing which you have to consider in measuring an FRA. This I will skip. So, and now we come to the tricky point. How should we interpret the FRA? I said before, you need somehow a fingerprint. So this is a time-based comparison. You have a transformer. You measure at this transformer the FRA after the factory acceptance test, and then some years later you repeat the measurement, same phases, same transformer, with the same setup, and then you can say, if this frequency now changed, we have a problem. But unfortunately, often this fingerprint is not existing, simply because after the factory acceptance test there was no FRA measurement done. So what can you do in this case? You can use a phase-based comparison, so you can compare the phases A, B, and C to each other. Of course, you have to take into account that the middle phase is a little bit different as the outer phase. So you have differences between inner and outer phases, but these differences, you know how they influence the frequency response. Or you can also do a type-based comparison. So maybe you have a sister unit which has the same design. You can measure there and compare these results. Of course, best is to have a time-based comparison, also phase-based. Type-based can be difficult, because maybe if the manufacturer has changed a little bit the design, you do not know this, and then you can get different responses, although the transformer is okay. And then you have two frequency responses, and let's say here are two units shown. If you look at the full frequency band, so this is up to 1 megahertz, both curves look pretty much the same. But if you start to zoom in, you see, okay, there are some differences. So, is this now okay, or is it not okay? You know, if the transformer is still in the warranty time, of course, the operator would say, this is not okay, and the manufacturer will say, it's okay, it's very fine. So you see that this visual interpretation is questionable, It depends on the point of view. So what we are looking for is an objective interpretation of these curves. And so we had a secret working group which, let's say, analyzed different interpretation schemes. Very shortly, we have here, let's say, the measured frequency responses of one transformer. We have here the frequency range from 10 hertz to 1 megahertz. And you can see here in the lower frequencies, the core is responsible for the response. Here in the middle frequency, it's interactions between windings. In the high frequency range, it's winding structure. And above 1 megahertz is more or less a measuring setup, which is influenced. So you know a little bit on which frequency bandwidth you have to check, and what if you have certain changes, let's say in this region, then you know it's the core. Here you know it's the winding structure. So, and what is now done is we apply mathematical formulas to both curves. These are the different formulas which are suggested in the literature. So X and Y are the two curves, and a lot of things are then calculated. I do not want to show you these formulas. You do not understand, even I do not understand all these formulas. Yeah, different researchers have different proposals, and everybody thinks his own formula is of course the best. Yeah, and we checked all these formulas. How did we check the? And the second point I have to admit, it is never good to apply this formula on the full curve. It's better to look at certain frequency bands. Yeah, so we just check the frequency bands of the core, of the interactions of the winding, the high frequency band of the windings, and we check what is the index at this frequency. Yeah? So we have here the full FRA. We investigate here the low frequency bands, the medium frequency band, and the high frequency band. Then we apply the formula, and then we have a final value. So 0.97 here for the medium frequency. So this is first an objective value. But of course now the question, what is a correct limit? So what should be the value for a good transformer, and what should be the value for a bad transformer? Yeah? And so we investigated these values based on a database which was collected by Segrest. So we had there 140 FRA measurements of different transformers, different mechanical deformations, and checked which indices is good. So it was in this case CCF, LCC, and SSE. Keep that in mind, maybe not that important, but most of these proposals are not good for an objective interpretation, yeah, because they have to monotonic, linear, sensitive, so there are different parameters which you can test for these indices. But the basic problem is still, what are the frequency ranges, the different frequency ranges which I should investigate? And this is dependent on the size of the transformer. You can imagine a big transformer has lower resonance frequencies as a small transformer. So these frequency ranges are dependent on the transformer size. And we suggested a new algorithm where we use just a sliding window. Yeah? So we move a window over the full frequency band and calculate, let's say, the value of the index in each window, and then this brings us this red curve, this green curve. Here are the, let's say, red and black are the two frequency responses which should be compared. And you can see here where they differ, then this function gives here this green peak. And if this green peak is below -5, we know we have a problem. So that we have also a certain limit. Some use cases. Here, conductor tilting. You can see here the conductor is not vertical, but it's a little bit shifted due to axial forces. This is the frequency response. Red phase A shows significant differences from B and C. And here, everywhere here where the red arrow is, and therefore you can see this transformer is not okay. And because of this FRA, this transformer was scrapped. Here we have buckling, a picture of the buckled transformer. Here again the FRA, and you can see here the green and red phase are really on top of each other. So we have here a phase-based comparison, and but the blue one is really different, which shows we have a problem in the blue phase. Here we used the sliding window technique, Yeah, here we have the two curves. Here we see also a major difference, but this is, as I said before, the low frequency, and low frequency is due to the core magnetization. So if you have a reminiscence of the core, then you can have a shift of this frequency. So this shift has to be disregarded. But here for the higher frequencies, we have here a value of -20, which is higher than -5, or lower than -5 in the negative range. That means we have a problem, and so the transformer was dismantled, and you could see here the buckling of the winding. Okay, so let's conclude with the FRA. It's it was in the beginning quite academic diagnostic techniques, but now it's already standardized. Yeah, so we have an IEC standard which describes how to perform an FRA measurement. And so normally during the factory acceptance test, such an FRA is measured since the last 5 to 6 years. But for the interpretation of the FRA, this standard up to now does not give any recommendations, and so Sigre worked out and gave proposals like I presented here. And so in future we can have an objective interpretation, and also they start now to revise the standard, and in the next revision of the standard there will these rules be implemented. Okay, let's come to the last point, PD measurement on a transformer. Yeah, time is good. What are PDs? PDs are partial discharges, and partial discharges appear if you have a very high electrical field strength on a certain position. For example, if you are standing on a high voltage line, you can hear this noise, this corona noise. Yeah? There are some small sparks on the transmission line, and these corona discharges are partial discharges. So let's say you have a flashover in the air very near to the high voltage electrode, but you do not have a full flashover to ground. Yeah, so it's just a partial discharge. And these partial discharges, of course, can also occur inside the transformer tank in, let's say in almost all positions where we have high electrical field strength. So here you can see an active part. You can have these partial discharges at the lead exits, also within the windings, at the tap changer. Yeah, so there are different possible locations of partial discharges. So you can measure these partial discharges by different means. Normally it is done by a dissolved gas analysis. Dissolved gas analysis means you take an oil sample from the transformer and you analyze this oil sample in a laboratory, what gases are in the oil, and dependent on the amount and type of gases you can decide, do I have a problem or is there no problem? So a problem can be a hotspot, partial discharge, and whatever. But of course this DGA does not tell you where the PD is, and also not how strong the PD is. Yeah? So it's just a very early indicator. You can compare it with, like, if you go to a doctor, he takes your blood, analyzes the blood, and then he says you have this and that, maybe. So now we have to do X-raying or another diagnostic technique. This DGA gives, let's say, the first view on the condition of your transformer. Yeah, but of course you can also measure PD electrically, because if you have a discharge, also currents are flowing. Very small currents, but you can measure these currents. Additionally, if you have a discharge, also electromagnetic waves are emitted, and you can measure these waves by an antenna, of course, yeah, like we have it in our mobile phones or here is a microphone. And also acoustic waves are generated. Yeah, as I said before, if you're standing on a transmission line, you can hear the corona. Yeah, same in a transformer. Yeah, there are noises generated, which you can measure by microphones on the tank wall. How do we measure electrically partial discharges? We have here the transformer tank, we have here the PD, and then this PD current is flowing through the conductor of the winding, and at the bushing you have a capacitance, and you can use this capacitance for decoupling of the pulses. And then you can measure electrically PD. This is done in a frequency range of 30 kilohertz to 1 megahertz. Problematic with this technology is that you also measure the PD which occur on the connected lines. Yeah, there's also PD. Yeah, and it's difficult to distinguish between this internal PD, which you want to measure, and these external PDs, which are, let's say, normal for a transmission line. So what we suggest is to use UHF sensors, which is an antenna, which is here inside the tank, and you measure the electromagnetic waves in a frequency range of 300 megahertz to 3 gigahertz. You can see this here. We have here an electromagnetic simulation of the wave which is emitted by a partial discharge. So we have here the partial discharge source, and each picture is 1 nanosecond. So the electromagnetic wave is migrating through the transformer tank, and here after 25 nanoseconds the electromagnetic wave arrives here at the antenna. The antenna detects these waves, and you can, of course, measure the output voltage of the antenna here with an oscilloscope, and then you get here such an impulse. And you can see here the transformer tank itself acts like a Faraday cage. So the electromagnetic waves cannot come out, but also electromagnetic waves from the outside cannot enter the transformer. So if you measure inside the tank electromagnetic waves, you can be sure that you have internal PD. So this technique is very immune to noises. During the factory acceptance test, you do a partial discharge measurement in the test field, but a test field is a very well-screened room, and there you do not have any noises. So for factory acceptance test, this technology is working pretty fine. But if you go on the outside, on-site in the substation, then you have to drink something. But if you go on-site, then of course you have a lot of noises. Yeah, you have mobile phones, radio frequencies, a lot of things which can disturb your measurement. but due to the shielding effect of the transformer tank, you can be sure if you measure the electromagnetic waves inside the tank, you have a problem. So how do the sensors look like? There are two types of sensors. These are so-called drain valve sensors, because you can install these sensors at drain valves which are installed at the transformer tank to release the oil. So you can retrofit these sensors. Yeah, they are installed here at the valve. Then you open the valve, and then you can push in the antenna here inside the tank. The others are so-called window type sensors. These are welded on the tank wall. We have here a dielectric window, and here is the sensor itself. The design of these sensors is more or less standardized also in a secret brochure. So such a sensor looks like this. of course, these sensors can only be installed in the factory, because you have to weld something on the tank wall. So this is the typical technology for new transformers. Of course, then is a question where to install these sensors. Again, we have shown here a PD which is inside the winding, and you can see first the electromagnetic waves have to come out of the winding. Yeah, here you see it's coming here on top, on the bottom out of the winding, and therefore we suggest to install the sensors above the upper end of the winding or on the lower end of the winding, because here the electromagnetic waves are the strongest. In total, we say the minimal configuration for a smaller transformer is 2 sensors, but for bigger transformers you can also install more to increase the sensitivity and also to localize the PD. Let me show you some use cases of these PD measurements. So in the beginning, as we presented this technology, some people said, the discharge in oil is too slow that UHF frequencies are generated. So simply there are no UHF signals. And this argument was always mentioned by the people who were supporting the electrical PD measurement. So and then we collected measurement results of different research teams. Yeah, and we these are, let's say, the use cases. It starts with quite small distribution transformers and ends with a 1000 MVA auto transformer, so a very big unit. And we collected these frequency spectra and wrote a paper on this, which we published last year, beginning of last year. And there were contributors of, I don't know, 8 or 9 different contributors from everywhere in the world, also from Brazil, which showed their examples of UHF PD measurements. And it shows in which frequency range they measured the PD. For example, here let's look here at this 333 MVA transformer. Yeah, there are frequency from below 100 megahertz up to 1 gigahertz measured. So a large frequency band. The dots here mean that at this frequency we have the highest emission, but more or less you can say that in the range of 400 to 900 megahertz, all PD emitted electromagnetic waves. Yeah, so if you measure in this frequency range, you can be pretty sure that you will detect the PD. First example shows the influence of external corona. So we had here a transformer and an offline measurement, so not the grid voltage, an offline measurement. The advantage of the offline measurement is that the noise is a little bit lower. And we measured here the UHF signals inside the transformer tank. Yeah? So this is the so-called the PRPD pattern. Then we added a strong external corona by fixing a wire here on the connection. And on this wire, of course, we had very strong corona in air, but the PRPD pattern was exactly the same as before. Yeah? So the external corona didn't influence the internal PDs. The reason is, of course, that the bushing here has a capacitance to Earth, and the high frequencies which are generated by this external corona have, due to this capacitance, a short circuit path to the ground and do not come into the transformer tank. Second example is a 400 kV unit, 50-year-old transformer, and with this transformer the operator detected hydrogen, which is a sign of partial discharges. Then he decided to do an electrical PD measurement. This was not possible because above the transformer there was the bus bar, and there was some, of course, PD on the bus bar in air, and these PD were so strong that you could not measure any electrical PD inside the transformer. So we installed UHF sensors. We have here 3 UHF sensors, here one at the bottom and here and there, because there were oil valves, and measured with these UHF sensors the signals. You can see here the responses on different positions. Here we have UHF sensor 1 is here, 2 is here, 3 is there. And you can see there are time differences between the signals. Time differences because the electromagnetic wave has to travel from the origin of the PD to the different sensors. Yeah? And you can see here it arrives first at sensor 2, then it arrives at sensor 3, and then it arrives at sensor 1. And from this information, you can already guess where the PD is. Yeah? So, of course, it must be nearest to sensor 2. And so we knew we are here in this region with the PD. And then we installed microphones on the tank wall of the transformer to measure the acoustic emissions. Problem with acoustic emissions is that the signal is very, very low. So if you do not know where the PD is, you will never find the correct positions for your microphones. But in this case, due to the location with UHF, we knew approximately where it is, and then we measured acoustic signals. Here, you can see such an acoustic signal. And what you can see here is noise. Yeah, this is more or less just noise, because the signal itself is so small. But we can use the UHF sensor as a trigger source. So we trigger the acoustic measurement by the UHF, and then we average a lot of signals, because with averaging you can reduce the noise. Yeah, and here we have now, let's say 100, 150 measurements averaged. Due to this average, the noise is decreased. You can see here the noise. And here now you can see also the acoustic signal, which is coming out of the noise due to the averaging. So we used, in this case, UHF for triggering the acoustic measurement. And then we have here, of course, the traveling time of the acoustic wave inside the transformer tank. And if you do this in different position, you can calculate the origin of the PD. Yeah, and the origin was in the region where the tap changer was installed, and you know the region of the tap changer can easily be accessible. Yeah, if it's within the winding, it's of course difficult, but in the tap changer region you can do some repairs. So the transformer was brought back to factory and opened, and here you could see, yeah, these dark spots on the tapping leads, and you know, if this PD would have been continued, then you would have a failure here, a breakdown, and a breakdown on the tapping leads normally means full loss of the transformer. So, and repair is quite easy, because you just have to exchange the paper here, you have to dry the active part again, put it back into the tank and refill of oil, and yeah, it's still operating, the transformer. But you can use this UHF also for monitoring purposes. This, what here you can see a full monitoring of a transformer, monitoring system of a transformer, and here this equipment here is the UHF PD monitoring system. One case of such a UHF PD monitoring I present here. This was a 123 kV transformer, and this 123 kV transformer had an internal flashover. So it was brought back to a repair factory, and they clean, you know, then you have, after such a failure, you have carbon deposits on the winding, and you have to clean it. But this repair factory didn't have a vapor phase oven, so they could clean the windings just by spraying oil on the winding and washing it, like you wash a car, more or less. Yeah, you do not use water, but you use oil to remove the carbon particles. But of course, you have also carbon particles inside the winding, which are difficult to remove. Yeah, at the end, they put everything together after cleaning in this way, and then they did the factory acceptance test. The factory acceptance test was more or less checking, is the testing voltage okay? So is there no breakdown during the test? But I said, we have also to do a partial discharge test on this transformer. And then they said, we cannot do a partial discharge test because our testing transformer is excited by a power converter. And the power converter, of course, has thyristors for switching of the converter. And these thyristor switching gives PD pulses, or let's say gives electric pulses, which are detected by the PD measuring system. Yeah, you can see these thyristor switching here with these, let's say, call it fingers. So you have here a noise level of 3 nanocoulomb, which is very high. Yeah? And due to this high noise level, you could not measure the internal PD of the transformer with an electrical system. So we installed here 2 UHF sensors on the transformer tank, and with the UHF sensors we could measure here internal PD on this transformer. And then of course there was a question, oh shit, we have internal PD on this repair transformer. What should we do now? Can we bring it back into operation? And then the operator said, okay, then I want to have a monitoring of these PD, that in case the PD is getting stronger, we can switch off the transformer. Yeah, so we installed the PD monitoring system. You can see here some results. In red, you can see the oil temperature of the transformer. In green, you can see the loading of the transformer. Yeah, so this is one day. Yeah, you have a high load during daytime, low load in the early morning. And the blue curve is a PD level. Here in this case, the transformer was switched off. Then you have, of course, a low PD level. But here you can see very nicely that the blue curve and the red curve are more or less in parallel. So PD behavior is dependent on temperature. Why is it dependent on temperature? You know, if the transformer is warmer, then the oil flow through the winding is higher because it's a natural cooled transformer. And if you have more oil flow, then of course you have also more flow of particles, which create these PD. You cannot see this without monitoring. I think this is one of the first examples which shows the behavior of PD dependent on temperature of the transformer. I can End of this story was, here is a longer time, so here we can see half a year of monitoring data, and in this case the green is the PD value, and you can see that the PD value is decreasing. In parallel there were also some DGAs with measuring the hydrogen content, and also the hydrogen content is falling. Yeah? There was a peak here, but then it is falling, and the transformer is still in operation, and PD was really reduced, maybe because the carbon particles somewhere are now in the region where no electrical field is, yeah, so moved away from the risky areas, so transformer can operate. So, long time. Now we come to the conclusion, because there's also lunchtime almost. So I explained you that PD is a mighty tool to ensure the quality of the insulation system. And if you apply this technique online, then UHF PD measurement has advantages, because it's quite immune to noises compared to electrical PD measurement. Yeah, and their online monitoring is possible in order to really to monitor the PD behavior dependent on different operational conditions of the transformer. That's it. There are a lot of more condition diagnostic techniques, but I spoke already more than 1 hour, and let's say we have in German the saying, you can talk about everything, but not longer than 1 hour. Yeah. So I'm at the end. Thank you for your attention, and of course I'm open for questions. Thank you.
So thank you, Professor Stefan, for your presentation today. It was really interesting to see the development and the studies you are conducting in SIGRE. And we have time for questions, for maybe 1 or 2 short questions before to going for lunch. Please feel free to hand your hand. And okay, we have a question over here.
Thank you for your presentation. First is a teasing question, because the title of your presentation says AC transformers, right? Are you opening a window for DC transformers in the future? We are talking about smart energy system. This is just, you don't need to answer, but
but I can answer this question.
My main question is, with smart energy systems, we have more and more interface transformers, not to the high voltage, but for medium voltage, interfacing power converters to the grid. And my question is, of these techniques and measurement systems that you apply on high voltage and high power, which one would be more suitable to evaluate failure and reliability of transformers for interface power converters? Thank you.
First answer, AC transformer. You know, as I saw the title of the working group, I thought, AC transformers, are you stupid? Yeah, because every transformer is working with AC. But it should distinguish between HVDC transformers. Yeah, you know, you have in HVDC links, you are also using transformers, and the reliability of these transformers is investigated by a different SIGRE study committee. And not to interfere with the other committee, we wrote AC transformer to distinguish between the HVDC transformers. Yeah? And you know, also in HVDC transformer, there's AC applied. Yeah, yeah. So that was the reason for AC transformer reliability. But what techniques are applied to, let's say, distribution or to lower voltage transformers? The problem is, of course, that such a measurement system or doing measurements costs money. And if you have a distribution transformer, often these transformers itself are quite cheap. And if you lose a distribution transformer, maybe you lose the power supply of a few households. But yeah, let's say, this is not so costly. Yeah? And therefore, these techniques are normally not applied to, let's say, these not so important distribution transformers. But here, in case of UHF PD monitoring, I had a case of wind farm transformers. So these transformers are located in the nacelle of a wind turbine. And these modern wind turbines have a rating of 5 MVA. So there's a 5 MVA transformer installed in the nacelle, so on top of the tower in 150 meters height. And there are several manufacturers of these wind turbines complaining that these transformers fail quite often. One reason for this is the sealing of the oil in this transformer. It's with a nitrogen seal, and this nitrogen is soluted by the oil. And once the load is decreased, the temperature of the transformer is falling down, and due to this, the nitrogen is creating bubbles. It's like if you have a sparkling water. If you open the bottle, then you have these bubbles, and these occur in the transformer, and then you have PD inside these bubbles. And you know, a 5 MVA wind turbine is much more important as the distribution transformer here on the road. Yeah, especially if, let's say, if you have a wind farm with 10 wind turbines and 5 have this problem. Yeah, and so they installed such a monitoring on these transformers to see what is happening, to investigate the effect of bubbling. So sometimes it is useful. Yeah, it depends always on the importance of the load which is connected to the transformer. Yeah, but basically you can also use this for medium voltage transformers.
Thank you, Professor Stefan. Do you have more questions over there?
Thank you so much. I would like to ask, from the presented monitoring techniques, which one is most effective? Also, what are the recent technological advancements to further improve the health of transformer, the reliability of transformer? Thank you.
Yeah, what is the best is a difficult question, because you have to define what is best. Highest sensitivity, lowest price, whatever. Yeah, you see, this is which technologies you apply is of course also dependent on the importance of the transformer. As I explained before, if you have a huge transformer which is supplying a lot of customers, and you have not a big reserve, not a spare unit, of course, then you can have to invest more money on diagnostic techniques, as in case if you have a big reserve and almost no load on this transformer. So it's difficult to say. But the minimum what you should do is dissolved gas analysis and taking oil samples of the transformer. Yeah? You do this periodically every 1 or 2 years. This gives you a first sign of a problem. And then you can apply, of course, also monitoring. Yeah? This partial discharge monitoring, of course, makes sense in case you have a transformer with PDs. There are also a lot of transformers without PD, so it's maybe not necessary to install now in each and every transformer a PD monitoring system, because it costs money. Yeah? But if a DGA says you could have a PD problem, then you have to retrofit such a system. So there is not a general answer on your question. What is the best way? I would say at least a DGA and taking oil samples and to analyze this oil. But there's also C-tongue delta measurements of the bushing, which is useful there. And FRA, for example, is done after a short circuit, or maybe if the Buchholz relay has tripped the transformer. Yeah, so something happened, then you perform an FRA. So difficult to give there a general answer.
So yeah, it's a really difficult answer. Yeah, you don't have just an answer. That's because you're continuing investigating, Professor Stefan, and you use a lot of ways to do that. So we are on time. I'd like to thanks to Professor Stefan for your presentation. Professor Stefan will be with us until Wednesday. So if you have more questions or you want to get in contact, please let us know and we'll do that for you. Thank you very much once more, Professor Stefan.
Thank you.
This is the
Obrigado.
This is a short gift, from the conference side. Thank you so much.